In lesson 1.4, we're going to be talking about polygons. Something that's important to know about polygons is that they are a closed figure in a plane formed by connecting line segments at their endpoints, with each segment intersecting exactly two others. Those segments are called the sides of the polygon, and the joined endpoints are called the vertices. So we have a couple other vocabulary words: sides. Oops, pardon me again. We have sides, and we also have vertices in the polygons. Down below here in the pictures, we have some examples of polygons on the left. So the three figures on the left, these three figures circled in purple, are examples of what polygons could look like. Just three examples. Notice that they all have straight segments for sides, and there's no crossing segments. It's a closed figure. On the right-hand side, we see some non-examples. In this pink circle here, the first one on the left is a non-example because some sides are curved. In the middle example, we actually have two different polygons. And in the third example, there's some openness that's not closed, and that's why those three things are not polygons. Now, some of the polygons have been named by math people, some of the smaller sided ones. For example, down below in the chart, you'll see that a three-sided figure is called a triangle. A four-sided figure in general is called a quadrilateral. There are specific ones like rhombus, square, rectangle, but the general term is quadrilateral. And so, as we look at some of the other figures, like a five-sided pentagon, six-sided hexagon, seven-sided heptagon, eight-sided octagon, nine-sided nonagon, 10-sided decagon, 11-sided undecagon, 12-sided dodecagon. These are some of the ones that you might recognize as you've heard names of polygons with different sides. They started getting bigger and bigger and bigger, and people just decided it was ridiculous to keep trying to name all of them. So then as they get too large to keep going on, they'll just say n-gon, and n represents the number of sides. For example, if I say I had a 67-sided figure that was a polygon, I would call it a 67-gon. Which is kind of lame, but that's just the way they do it because they didn't want to name every single figure that was out there. So just for your information, that's how it works. In this next slide, we're going to talk about how to name a polygon. So first of all, you have to name the vertices in consecutive order. So the polygon that's on the left-hand side can be named many, many ways. So for example, if I wanted to, I could name the polygon A, B, C, D, E. I could also start at C and go C, D, E, A, B. I could have gone with C and gone the opposite way. C, B, A, E, and D. I can do it any way I want to as long as I start at one vertex. I either continue clockwise or counterclockwise in order. I cannot, I repeat, in no way go out of order. For example, I can't name it A, C, B, E, D. That's not possible. So you'll usually see the symbol next to it, and then you'll see the actual letters naming it. And remember, they might name it differently than you, but could be talking about the same polygon. So this triangle here down below, highlighted in green, is named triangle ABC by me. I could have also named it triangle CBA or CAB. It may have numerous names, but it has to be in order. Any one of the names is fine. Down below the naming of these polygons, you need to know the definition of what they call a diagonal. So a diagonal of a polygon is a line segment that joins two non-consecutive, which means not in a row, vertices. If all of the diagonals are inside of the polygon, it's called convex. If even one one diagonal is outside, it is called concave. So down below here, we have concave polygons because I notice that I have some diagonals that are outside of the polygon. So these red lines are the diagonals. Whereas if I look on the examples in the convex polygons to the left, what I notice is that all of their diagonals fall inside of the polygons. Like for example, on this rectangle looking thing on the right, and the pentagon that's in the middle, also in the hexagon, there are a lot of internal diagonals here. You'll see all of them. Notice how they're all inside the polygon. So if they're inside all of them, that's called a convex polygon. If even one falls outside, like the ones on the right, the last two, then it's called a concave polygon. Some other vocabulary that we're going to be working with is, first of all, the word equiangular. That means all angles have the same measure. And we also talk about equilateral, which means all sides have the same measurement or length. When you have a polygon that has both of those situations, that's called a regular polygon. So for example, down below, what you'll notice is that we have a first figure on the left that has 4 equal angles. That's why it's equiangular. Probably a rectangle looks like. The second figure is what they call an equilateral figure because all of the sides are the same length. You can see the markings on them. And that's probably a rhombus. And then the last figure is a regular polygon because it has all angles equal and all sides equal, which means it's probably a square. When you're trying to work with congruent polygons, especially when they're not triangles, you have to know that there are certain things that are very important. So in order to be a congruent polygon, as you see down below, that's only going to happen if they're exactly the same size and shape, meaning that they have the same angle measurements and they also have the same side measurements. And so as we look at all of these figures, one of the things that you need to know is that both A and C are congruent because we can see that they have the exact same measurements. So we'll notice that they each have 2 right angles, that they each have 2 135-degree angles in the same ordering and a 95-degree angle, that the sides on either side of the 95-degree angle are congruent, and the ones in between the 135 and 90-degree angles are congruent. So I know that A and C are congruent to each other. However, even though we notice in B and D, that all the sides match up, we don't know about the angles. So we cannot say that figure B and figure D are congruent because we don't know about the angles. Whereas in the blue ones, A and C, we knew both about the sides and the angles. So something that's really important about congruent polygons is both sides and angles must match up, not just one or the other. Oh, I think that's it.